Hello students, welcome to today's lecture where we will discuss about stationary circuit variables transformed to arbitrary reference frame. In this particular session, we will see about the different elements like a resistive element, inductive element and the capacitive elements, and we will see how such elements are transformed from a reference frame to an arbitrary reference frame. So for a three-phase resistive circuit, V of ABS of the stationary circuit, so we have subscript S. So V ABCS is equal to RS into I ABCS. Now, as we have seen before, that we use a constant Ks, which is multiplied to the ABC term if we need to convert it into QD0 term. But here we need it in ABC terms. So this could be written as Ks inverse of V of dQ0S, which is equal to Rs, and again I is in ABC terms. So we'll multiply Ks inverse into I of QD0S term. So now we need to convert this ABC into dQs. So we already have V of QD0 here. We simply need to take this term, that is QS inverse term, on the right hand side. So that becomes, sorry, KS inverse term on the right hand side, which becomes KS. So Q of dQ0 is, I'm sorry, V of QD0S is equal to Ks into Rs into Ks inverse into I of QD0S. All stator phase winding of either a synchronous or symmetrical induction machine are designed to have same resistance. Similarly, transformers, capacitor banks, transmission lines and all power system components are designed on that all phases have equal resistances. The power system load are also distributed amongst phases so that all phases are loaded nearly equally. So we have seen that we always try to keep all the loads and all the phases equally so that the power system balance is maintained. And if the non-zero element of the diagonal matrix Rs are equal, then Ks into Rs into Ks inverse is equal to Rs. Okay, now this is only and only possible if the non-zero element of the diagonal matrix of Rs are equal. So this is basically a simple rule of mathematics that if the non-zero elements of this component is equal, the non-zero elements of the diagonal matrix are equal, then and then only this could be neglected, and what we have the result is Rs. So if the phase resistance are unbalanced, the transformation yield constant resistances only if the reference frame is fixed, where the unbalance physically exists. So the resistance matrix associated with the arbitrary reference frame variables is equal to the resistance matrix associated with the actual variables if each phase of the actual circuit has same resistance. If the phase resistance are unequal, then the resistance matrix associated with the arbitrary reference frame contains a function of theta. So it would contain a function of theta where Ks is algebraic. It means that The transformation gives constant resistance only if the reference frame is fixed where the unbalanced physical exists. The feature is quite illustrated by substituting the Rs, which is equal to the diagonal of RAS, RBS and RCS into Ks into Rs into Ks inverse. Next, we'll move to the inductive element. So, for a three-phase inductive element, we have V of ABCS is equal to P into lambda of ABCS, where P is nothing but an operator which is a d by dt operator. In this case of a magnetically linear system, it can be expressed that the flux linkage as the product of inductance and current matrices before we perform the changing of the variables. So here V of QD0S would be equal to Ks into P into Ks inverse into lambda of QD0S. Now this is the same that we had done prior to this, where V of ABC of S can be taken as Ks inverse into V of QD0S. The Ks inverse is taken on the right hand side, so it is Ks here. P is as it is, and lambda ABCS is converted, which is equal to Ks inverse of lambda of QD0S, and this is how this equation has been transformed, as we have seen in the resistive element case as well. Now let us further solve this equation. Ks into this P is nothing but my d by dt, and d by dt of the two terms. So I take d by dt of the first term and let my second term remain as it is. So my lambda of QD0S remains as it is, and d by dt of Ks inverse, that is my first term, plus Ks is as it is, Ks inverse remains as it is, and d by dt of my second term now, so that is lambda of QD0S. So again, if you look at the annexures and if you see, then you will be able to get the clear indication of d by dt of Ks inverse, which is nothing equal to omega into minus sine theta cos theta 0 minus sine theta minus 2 pi by 3 cos theta minus 2 pi by 3 0 and minus sine theta plus 2 by 3 2 pi by 3 cos theta plus 2 pi by 3 and 0. And if you see the first term here, which is Ks into d by dt or P into Ks inverse, so this is nothing but omega into 0 1 0 minus 1 0 0 and 0 0 0. So I recommend to see the appendix A for further clarification on the trigonometric identities used in attaining these equations. So now again we'll return to this particular equation. We have Ks into P into Ks dash. So, and we simply substitute this values here. So what we are left with is omega into lambda dqs plus p into lambda qd0s. Here we have omega into lambda dqs. So here there is a mistake. It should be a lambda dqs instead of qds. So lambda dqs transpose is nothing but lambda ds minus lambda qs and 0. So the equations are often written as V of Qs is equal to omega into lambda ds plus p into lambda Qs. V of ds is equal to minus omega into lambda Qs plus p into lambda ds, and V of 0s is equal to p into lambda of 0s. So as seen in the VQS and VDS equations, the first terms in both the equations are based on the speed of the reference frame, or let's say the angular velocity of the arbitrary reference frame, and that is why these terms are also referred as speed voltages. That means these particular terms, the first terms of the VQS and VDS, would be 0 when my angular velocity is 0. Thus, from the above equations, we can say for a linear magnetic system, the flux linkages may be expressed as lambda of ABCS, which is equal to Ls into I of ABCS, where the flux linkages in the arbitrary reference frames may be written as lambda of qd0s, which is equal to ks into ls into ks inverse into I of qd0s. Here again, ks into ls into ks inverse would be equal to ls only when the non-diagonal terms or the non-diagonal elements of the matrix LS are equal. So this is the matrix of LS. Now if you see, all the non-diagonal terms are minus 1 by 2 LMS. In this particular matrix, the term LLS is nothing but the leakage inductances, whereas LMS are the magnetizing inductances. So a matrix of this form could describe the inductances of balanced three-phase inductive load, a three-phase set of line reactance used in high voltage transmission system, or any symmetrical three-phase inductive network without inductive coupling between the phases. In the last equation is for a symmetrical system where Ks into Ls into Ks inverse gives a diagonal matrix with the value LLS plus 3 by 2 LMS. And this is because it magnetically uncouples the substitute variables in all the reference frames. And now finally moving to the capacitive element. So again, I of ABC is equal to P into Q of ABCS, where Q represents the charge. Again, substituting the same things, here it has to be Ks inverse into I of QD0S. Ks inverse taken on the right hand side becomes Ks. P is as it is, and Q of ABCS is taken as Ks inverse into Q of QD0S. Now, this could be further written as we are taking P is nothing but d by dt, so d by dt of the first term. So Ks into P into Ks inverse, and the second term remains as it is, that is Q of QD0S, plus Ks into Ks inverse, first term remains as it is, and d by dt or P of the second term, that is Q of QD0S. So on further writing this, we can write this as I is equal to QD0S, which is equal to omega into Q into dQs plus P into Q of QD0S. We have already seen this in the inductive element, that why are we writing this as omega into Q of dQs instead of QD0S, where Q of dQs transpose is nothing but Q of ds minus Q of Qs and 0. So if we expand this further, if we expand these equations further, we have I of Qs, which is equal to omega into Q of ds plus P into Q of Qs. Again, I of ds is equal to minus of omega into Q of Qs plus P into Q of ds, and I of 0s is equal to P into Q of 0s. So similar to the terms used in the inductive element, here we see the first two terms of the equation IQS and IDS. The first terms of both the equation are again speed dominant. So in inductive term, we had represented, or we had called this term as speed voltages. Here we refer to these terms as speed currents, and needless to say that these currents or these speed currents would be zero when your omega or your angular velocity is zero. So hence we can say that for a linear capacitive system, we have Q of ABC is equal to Cs into V of ABC. And if you want to convert this into arbitrary reference frame, then Q of QD0S is equal to Ks into Cs into Ks into V of QD0S. So today we saw about how different elements could be represented in the arbitrary reference frame, and the resistive element, inductive element, and finally the capacitive elements, and how they could be represented in the arbitrary reference frame. So that's it for today's lecture. Stay tuned for the further topics of this particular uh, subject. So if you have any doubts, feel free to contact on the email address given in the description box. Thank you and have a great day.